Today's lesson is looking at three sort of specific cases that we may encounter when trying to look at uniform circular motion problems. Um, no new concepts, just three applications. The first application is maybe the idea of swinging a pendulum. When the object gets to the top, there's at some point where if it's not going fast enough, that pendulum will fall down. It won't stay in circular motion. Another case is a car driving over top of a curve, and if you go fast enough, the person inside the car may feel weightless, like as if they're floating in air. And then the third application is the idea of cars going around banked corners. So previously we looked at objects going around in a circle, like the ladybug on a record, where friction supplies a centripetal force. It's also the case where a car can go around a banked corner where the bank, or actually it's gravity, supplies the centripetal force. Or not the gravity, I guess the normal force actually. Okay, let's go through an example here with a car running a curve. So the basic understanding to really look at this is we need a half decent free body diagram. Doing a good free body diagram helps explain to us what's going on. So here's some scenarios. Here's the first one where we have a car, say it's going slow, its speed is slow. It has some sort of force of gravity. Oops. And let's suppose it's going really slow, like barely moving. So in that case, the normal force would be almost the same as the force of gravity. And when you add those two vectors together, you get the centripetal force, which will be very small. Now let's suppose this car is going medium fast. So the force of gravity, or its weight, is the same. Now the normal force is a lot less. And the centripetal force gets larger. Then we can continue thinking about this. So this is kind of like the idea of sort of like a thought experiment. Now we're going fast. The force of gravity is the same, but the normal force is even getting smaller. Centripetal force is getting larger. And then finally we get very fast. And at this point, we're going so fast that the normal force is almost nothing. Or, I guess for people who have taken calculus, it's the idea that the normal force is approaching zero. So normal force gets close to zero. And what will a person feel when there's no normal force? Well, they'll feel like nothing's holding them up. So that's the idea of weightlessness. You will feel weightless if there's no normal force acting on you. There's going to be gravity acting on you. There's always gravity acting on you. But you'll feel weightless if there's no normal force. Some of you, I'm sure some of you have experienced that, like riding your bike real fast, going over rolling hills and stuff like that. You kind of get that feeling where it feels like your stomach is jumping up. That's kind of the idea of weightlessness. So eventually your normal force is so small that you feel weightless. However, your force of gravity never changes. You never are weightless, okay? This type of question is similar to questions asked about speed required to keep a mass from falling when upside down. Just as the normal force drops to zero is when the mass falls. So that's the example we're going to do now. Just as an interesting side note, this sort of idea where a car is rounding a curve or at a high speed, that's actually how, I don't know if they still do it, but they used to test astronauts for weightlessness by doing this. So what they do is they would get into a large jet, I think it might even be like a 747, and the plane would fly, they'd go up kind of high, and the plane would go really fast and enter into some sort of arc like this. And while the plane was in this area here, the astronauts would basically feel weightless, so they'd be floating around inside the body of the plane because they're basically in free fall at the same rate as the airplane. Perhaps if you guys are interested in that, we can talk about it again another time. Okay, so the example here is that you're riding on a bike on a track that forms a vertical circular loop. What diameter of the loop is, if the diameter of the loop is 10 meters, what is the minimum speed required for you to make it around the loop? So a picture of that is this. This is like like a roller coaster kind of idea. Here's a loop, and say we have a cyclist riding a bike. So the cyclist is going around a corner like this, or the loop. And so we can draw the free body diagram of the cyclist. There's Fg and Fn. Those are the two forces acting on the cyclist. And we can say that Fc is Fg plus Fn. So the cyclist needs to be going a certain velocity in order to go around the loop. At some point, if v is too small, the bike will fall. In other words, Fn will go to 0. If there's 0 normal force on that cyclist at that point, that means the cyclist is not in contact with the track, which means the cyclist will fall. So it's kind of like we have, so we'll have, therefore, Fc will equal to Fg plus 0, or Fc equals Fg. So we just use some of our equations to solve this. So at this point the physics is sort of done. Now we're doing some math. Fc is mv squared over r equals mg. Masses cancel out. So we have v equals square root of rg. V equals, I guess we're at 5.0 meters, 9.8 meters per second squared, square root, and we get V equals 7.0 meters per second. So anything excuse me, anything less than 7 meters per second, and that cyclist will not make it around the loop. And the mass doesn't matter. It doesn't matter if it's a cyclist or a car or a bucket of water or whatever it is. If you have some sort of circle with a 10-meter diameter, whatever the object is that's going around that circle needs to be going 7 meters per second or it will not make it around. Alright, let's go to the next page. So this next part is looking at banked corners. Again, nothing new. We're just combining several different aspects of Physics 12. So it could include friction, inclines, vectors, gravity, normal forces, centripetal acceleration, all sorts of stuff. We're not going to spend a lot of time on bank corners, but the basic idea works like this: is that if you look at the free body diagram of this car, it has gravity pointing down, normal force acting out, or upwards, I should say, and there could also be friction. There could be some friction in here as well. It gets pretty complicated when we start looking at friction. So if no friction, we have a free body diagram that looks like this. Fn, Fg. Now, if our center of rotation somewhere out here, so the car is like coming, wow, I can't show you with my hands. Like the car is coming out of the page and going in a circle. Fc will be this. Fc will be that component of Fn. So that's Fc. So Fg doesn't do anything to supply Fc. I mean, it sort of does, right? Fg leads, the force of gravity leads to the normal force, and this horizontal component of the normal force leads to the centripetal force. Just to give you guys a better idea of what angle is what, I'm going to redraw a banked corner, and I'm going to exaggerate it, because when you exaggerate things, it becomes easier to see what the angle is. So let's suppose this angle is theta. That means this angle is also theta. Okay, let's use that information to try an example question. What is the maximum speed for a car rounding a 125-meter curve on a highway under icy conditions if the banked angle is 20 degrees? So we have theta is going to be 20 degrees. We can redraw that diagram, but it's basically the same. We have Fg, we have Fn, that's theta, and this is Fc. So we actually end up with a couple equations here. First one is that Fc is equal to Fn sine theta, and we also know that Fn cos theta is equal to Fg. So that's this idea here, that this component, maybe we could even call it Fny. Fny has to be equal and opposite to Fg. Otherwise, the car would either be floating upwards or sinking downwards, and we know that's not true. It's balanced vertically. So Fny equals Fg. So that's this guy. So let's take these two equations and work through them a bit. So this guy, we end up with mv squared over r equals Fn sine theta. And here we have Fn equals mg divided by cos theta. So we can sub 2 into 1. So we go mv squared over r equals mg cos theta times sine theta. Masses cancel out. So we get v equals rg tan theta square root. Oops. Oh. And then we get v equals, what was the radius? 125? 125 meters times gravity times tan 20. And I hope that all that equals, what's the answer? I can't scroll up here. Here we go. All that should equal 21.1 meters per second.